one.
Right or no?
No, I don't think there's a plan restriction.
Okay.
Right.
I don't think we have a plan. Is there one? Let's just let me like a recap or something we need.
He says he's doing guest lecture downstairs. He's doing guest lecture downstairs.
Like, but what do you have planned for today?
I don't know.
Slides?
Yesterday.
What?
Like he said, so.
Oh, you mean the guest lectures like during that?
Right now.
Wait.
Yeah.
Oh, okay. Well then, do we have slides we can just do?
Yeah, I made a bunch of slides.
Oh, okay. Great.
Okay.
Okay, I don't know.
All right. There's the camera. Okay. All right. Should I begin? Okay. Hello, everyone. Welcome to the final lecture for deep learning. All like 6 of you are here today. I think there are a bunch on the slides, on the online section too, who are watching right now. But wait, the slides aren't showing yet. It's yeah.
Sorry.
And yeah, so we've managed to have 5 lectures about reinforcement learning. We have 4 that didn't cover anything about neural networks, and about half of this one also wouldn't. But at the end, we'll finally get to the deep part of it, and then you'll be satisfied. And so I have to point this way, right? I'm new to this. Oh, it's this thing, yeah. All right, cool. So basically what we've shown so far is supposing that you knew everything about your Markov decision process, you knew the probability, yeah?
Will this lecture talk about the newer model and the trend?
Newer models, no plans to, but then I could ask questions. I can answer questions maybe
Because
about
the
this.
syllabus said they will talk about more, not reinforcement, not RL.
It may have been a bit outdated.
Okay.
But if you have questions about it, you can ask later. All right, cool. And so, wait, how did it go that far? And so, like, remember that for our Markov decision process, remember that we started on this model-free approach where we're starting to figure out what we can do when we don't know the transition probabilities or the rewards, and we're trying to figure it out just by exploring the environment instead of just using our ready-made numbers. So we have our really trusty splitter and the flighter and the spy, I think, example, where the spider moves around on the cube and it catches the fly after several turns. The fly might move around, but then we don't know, so we have to play the game to figure out what happens. And so far we've done a model-free prediction, which is we know what policy to use. Our spider is going to always move closer, or it'll always move away or something. And given this, how can we find out the value? So we've talked about methods like the TD1 and the TD lambda. And so in a bit, we'll be going into the model-free control, which is the part that everyone's actually interested in, which is how do you find this policy in the first place? But just a little more recap. We've had the Monte Carlo learning approach, which is just sample the episodes and take like the unbiased average, like the mean of all different trials and something like that. Whereas we have the more like DP, like temporal difference learning approaches, which like estimate values using kind of using previous known values of the values. And so remember that we've used the interesting trick with alpha, where before we took the mean directly with the formula that's shown on the top left. Let's see if this has a laser. Yeah, this one. And then we've basically shifted things around 1/k to a fixed number, and that basically gives us a kind of moving average, which can be, it'll like average. It's a biased estimate, but then it's good enough for our purposes. It'll basically find the average. And remember, for TD1, we have this kind of update rule where we're starting with a value, and then this is basically a delta term where we estimate we make an updated estimate of that value, which is the reward plus a discounted future value over here. We subtract it from the current value, and then we do the average update to basically get a better estimate of this value. And this is our TD1, which uses just one update in the future to predict the updated value for this v function. And this one works on an online setting, because like even if the game never ends, even if you just keep on going, your values are still going to update and you'll get better results. And remember that we've done a TDN, which is instead of looking forward just one step, we take several steps in the future. We sum all of those rewards with the appropriate discounting. And then finally, at the end, we bootstrap off of our previous estimates, which is going to give us kind of a more varied estimate, but also it relies on our previous values less. And we have this interesting approach that's called TD Lambda, which is where you have a weighted average of TD1 and TD2 and TD3 and so on, all the way until the end. And then in doing so, we have we have the best of both worlds, or we kind of are allowed to tweak Lambda to make a trade-off. And we have the way we do this with an interesting way with the eligibility number, which every time you encounter a state, the eligibility kind of increases by 1 up again. And then every time we don't encounter that state, it becomes less and less eligible. We're multiplying by this lambda gamma term, which makes it smaller and smaller. And so like every time we get into a new state while exploring the environment, we're going to update the values of everything else. And the amount we update it depends on how eligible it was, which is this E number. So over here, we kind of do the same thing, which is the value plus alpha times the delta number. And now it's multiplied by the eligibility. And the delta is basically computed in the same way. And so in doing this, we kind of like, we're able to average over all of the different TD rules. And then we can like tweak the value of lambda to see how much do we care about the previous, how much weight do we put on to the far past vs the recent past and so on. Is there any questions up until now for the recap? Okay. So now we're going to talk about the model-free control, which is how we're going to actually find out what we need to do, like what is our policy. But then to do this first, we have to kind of get into a short digression about the action values, which is previously we've basically focused on the value of a state, which is easy to understand. Like you want to be in this state, you don't want to be in that state. You want to go to states that have high values and so on. But the thing is, with kind of the control methods, there's a construct that's better than the value. We call it the action value, which is we assign a value to a pair of things, which is both the state and the action you're about to take at that state. So you're saying the optimal action value of something is like how much value you can get starting at a state and taking that action, and assuming you do everything optimally after that, for example. And so with just the value function, we hit kind of a big snag, which is even with the optimal values, how do you predict what next state to do? If you had the model, then it's easy. You say, OK, let's find out what the probabilities of going to each state are if I take this action. And then I average over all of those probabilities multiplied by the values and figure out which one had the best value and take that action. The thing is, with the model-free approach, we don't have the probabilities. If we just have the values, we basically can't do anything. We can say, OK, I'm in a bad state, but I don't know what to do. Oh, I'm in a better state, but I still don't know what to do. And with the action values, we can, like, now that we know how good it is to take an action at each state, we can take the argmax and find the best action at that state. And so the optimal policy will be the one that uses the action that has the best action value at each state. So knowing the action values, you can find the optimal policy. And so just yeah, this is basically the mathematical notation, where before our policy using the values required us to know this probability term and also rewards. And so if we want to do it model-free, then we're going to have to estimate both the values. I'm going to have to estimate the values, the probabilities, and the rewards. It's going to get very tedious. But with action values, you just have to argmax the actions of the action values. And we'll be able to do it immediately. So just to make it clear how we can actually do action values, it's pretty easy how we can implement TD1, TD lambda, and so on with action values instead of values. And so before with TD1, we initialized the values all to basically an arbitrary value, 0 over here. Over here, now instead we're storing all of the action values, which we call Q, which is a function of both the state and the action. And then for every time, we're going to first pick an action according to our current policy. And then we calculate a delta, which is the reward we got when we were exploring the environment, plus this term, which is like the discounted future reward. First of all, we're going to take that future action at that future state and discount it, plus the reward. That's the future return. We subtract it from our current return. That's going to be our delta. And then we basically update it the same way as before. We multiply by alpha, and we add the delta in. So any questions about how we can do the action value? Very similar with TD lambda. We have an eligibility term for each state action pair instead of just for each state. And the same way, the eligibility decays by lambda gamma every time. And then we add in 1 for every time we reach both the state and take that action. And then we sample the next action. We find the future return, subtract it, and then do the updates, scale it by eligibility, so on. Same old TD lambda. We're just using action values instead. And so now with that cleared out, we're going to talk about optimal policy. How we're going to find the optimal policy given basically almost nothing known about the environment. So just like to formalize what the problem is, we're just given this data. Or first of all, we're given we're knowing what states and actions exist, and then we go through the environment and we figure out we're in this state, we take this action, we end up in this reward, and so on. We get this episode, we call it, this string of state actions and rewards. And then to find the optimal policy from this, where we have to basically use the data to compute what the best action values are. And ideally, we do it online, although there are uses for methods that are not online either. And so for policy iteration, which is this is for planning, by the way. Policy iteration is not model-free. But remember that in policy iteration, we started with a policy. And then what we did is we computed the value of that policy. And then we improved our policy using those values, which with this kind of Bellman equation. We do a greedy update, which is first we find like a kind of estimated future values using the rewards and the discounted future reward, the discounted future return with our kind of current estimates of the values. And then we do the greedy argmax on top of that. And if we do this enough times, it will actually converge to the optimal policy. But this is, again, only works for planning. Can we do this for model-free control instead? Anyone want to propose like a trivial update to this algorithm that would possibly make it work for control? We have so like this one, we used kind of yeah?
We can pick the one that maximizes with random probability.
What'd you say? Do you get the one that maximizes the probability?
Oh, with random probability, pick the one that maximizes the value.
Is it this term? So like, if this term is just math, so there's no real like sampling required. You don't really have to do a random probability. You can just find which one is the argmax. Although like this term over here is an estimate of the value, so that's like why we have to do an iteration. Oh, so yeah, you're saying, first of all, we turn these values into action values. That's great. That's one step toward it. And the other is actually pretty trivial. We can just, instead of using the old method of computing the values, using either DP or using like linear algebra, we use our TD lambdas approach, which is basically designed to help us find values or action values using a policy, even if it's model-free. So this is our proposed algorithm. It's very similar. We use TD learning or something to find our action values. And then we use the argmax over the action values to find the policy, the updated policy. And then we do this over and over until supposedly we hit convergence. Now, let's see if this works with just a practical example. Here is a grid world. It's a very common educational reinforcement learning problem, where over here we're starting at this kind of blue square on the top right, and we're allowed to take one of 4 actions. We can move up, down, left, or right, and every time we choose the action, it will always move us there. Some variants are kind of probabilistic, like sometimes you say you want to move left, but then probabilistically you don't move left. In this case, it's deterministic. If you move left, you move left. If you start on the top right corner, you take the actions, and the game ends once you end on the green corner. It turns out that we're going to accumulate a lot of negative rewards during the process. You can think of those as distance. You don't want to move very far, and you don't want to spend a long time moving. But then I'm not going to tell you, this grid is not to scale. I'm not going to tell you, how long it takes to move between the squares. Instead, we're going to try to use a model-free approach to see what happens. So this is the first iteration. Let's suppose our initial policy is just choose randomly to go move up, down, left, or right. And we're going to see if we can get a better policy out of it. A little spoiler, this is what the optimal route turns out to be. But with our random policy, you see you're going to get really bad paths. You're going to backtrack all the time, or you're going to take really long detours. But first we have to play several episodes of this to get our data. And then while we're doing this, we can use TD learning to estimate the action values. So for each state, we want to figure out what's the value of going up, down, left, or right. Using TD learning, we're going to, with enough samples, we get a pretty good estimate of all the values. And then now we do the greedy policy, where this greedy policy I made just based on these 4 samples. But even then, you can see it's pretty good. It's trying to move over here. And in the middle, it's usually going down or left. There's this weird one that goes on the right. Now, even with a lot of samples, you might sometimes have action values that have no samples in them. Like this top left corner, we've never visited it. We don't go up, down, left, or right on it. So we're indifferent about it. And in other cases, maybe over here, we've only ever moved down from here. So we can't really evaluate what the value of going left, up, or right is. So the argmax is only going to be argmax over down. And so the only option we have is down. But that's kind of like an implementation detail. The general idea is that we do this argmax and we get a better policy. This one looks pretty good. Now let's do it a second time, and hopefully we converge, right? Well, not so much. So if we follow our kind of algorithm naively, this is what our new samples are going to look like. Because we have our policy, right? So we had our old policy, which means we always move here, and then we always move there, and then we always move all the way down. There's kind of no variation to it all. We're using the policy we have previously, and then we're always going to take the exact same sample data. And now with our argmax or whatever, we're going to end up with basically nonsense for our new policy. What just happened?
But that is an optimal route, same number of steps.
Well, it's not the same distance for all of these. It turns out you can imagine that the whole thing was squished vertically and stretched horizontally. It's just that we don't know what the actual distances are. But the actual optimal route is this. There's no better one. And so, does anyone have a guess for what went wrong over here? Or what can you do to fix it? I mean, even if you run this a million times, they're all going to look like this. Because we said it's deterministic. Even if it's kind of probabilistic, you still have kind of very little variation. Most of your paths are going to look basically like that. So have any of you heard of exploration vs exploitation? So over here, we're exploiting the policy we've learned previously. We're not trying anything out, and therefore we have no idea how good any of the other policies are. So basically what we need to do is make sure we explore more of the different paths, just enough to figure out whether our path is good enough or not. And so with our policy iteration, we didn't have to think about this because we could update all of the states at the same time. We know the rewards, we know the transition probabilities, even if our policy never visits them, we can still figure out what the value is at that state. Whereas our model-free control algorithm doesn't get that luxury. It has to sample the data to basically figure out which states exist and, well, to figure out what kind of rewards it can receive by moving in various states. And so if your policy only takes you through these states, through like a small number of states, you only learn about the small number of states. And so the solution, like the kind of quick and easy solution to this is to use an epsilon greedy approach, which is normally we follow our policy because we still want to learn about the optimal path, or we want to like use the optimal path. But sometimes we do kind of a random variation of that. Like instead of choosing what the policy told us to do, we randomly choose one of the other actions. And that way, like over time, you can prove that if you run this infinitely many times, you'll be trying all the actions at all the states. You can, as long as the state transition probability matrix doesn't have like zeros in it. And so this leads us to kind of a family of model-free control algorithms. This is kind of the model-free variant of Monte Carlo, which is, first of all, we start off with a random policy, and then this is the same update rule as the Monte Carlo for prediction. And then after each episode, we also update the policy. This is the part where it's different from the previous Monte Carlo prediction algorithm. So before we just keep processing episodes, we don't change our policy. In this one, for each policy, we change our policy. For each episode, we change our policy, and we use the epsilon greedy approach that we've talked about earlier. And so we keep doing this. After each episode, we get a better policy. We run samples on that policy, and so on. You can show that this will converge to the optimal policy, or it'll converge to kind of an epsilon greedy variant of the optimal policy, more like, which is, I guess, sort of similar. We'll be getting back into how we can actually address that problem later. But so looking at this GT term, where originally this GT term requires us to finish the entire episode and like collect it empirically. But remember, with TD learning, we can actually bootstrap our estimate of this with our previous values for the previous value and action value functions. And so this leads us to kind of the model-free control analog to TD learning, which is called SARSA. And so in TD1 SARSA, what we do is we just use our previous estimate of the Q values to update our policy. I'll be giving an example over here. So we initialize our Q values, and then we take our actions. After every transition, we're going to update our policy. This is the part that's different from regular TD learning. And again, we use the greedy policy, which we take the argmax of the Q values to determine what's the best action. And then we do the update the same way as before. Does anyone have questions about how SARSA works? It's called SARSA because, like, first we start at a state, then we take an action, then we get a reward, and we have a new state, and then we predict our future action over here. So it comes in that order. And so this is actually pretty similar to our proposed algorithm. The only difference is that we do the greedy updates to our policy after each action. So instead of computing the entire value of our policy and then updating our policy, we're kind of like updating our values once and then updating our policy immediately after. And with this approach, we actually don't have to store the policy. It's kind of implicit in our queues. We can just, by just doing argmax of Q, we figure out what our policy would have been at that point, because our policy is always up to date. It's always directly computed from our current estimates. And then again, we can do it in like a TD lambda way, where we have an eligibility for each state action pair, and then we update accordingly to like the same way as the previous TD update rule that we've shown. And yeah, just to be more specific about how it works, this is kind of the update rule. Now, so we can take a closer look kind of at what it's actually trying to do. So again, we start from a state in action, we get a reward, we get to a new state, and we choose the next action, and we do the TD rules to update. But the thing is, it's kind of redundant, right? We have the second A over here. This A, like this SA kind of lines up with the future, the SA over here. Although the second S is not all that redundant because it is the same value of the S, but then we're using it to update the values, so it's a different meaning. For this S, it means we're currently in this state, and then we take the action. For this S, it means we know what next state we are. We're going to update our values with it. Very similarly, with this A, this is the action that we're currently going to take, and this A is the action that we think we're going to take at the next time step. So we can't really change anything about the second S. If we're going to be in like state C after the next time step, we're still going to be in state C at the next time step. We can't change that. But the thing with this A is that we only think we're going to be taking that action at the next time step. We'll be given like a second chance to choose that action at the next time step. And so I'll be showing you kind of more detailed what's happening. The question is like, how do we pick the second A that we use to predict our optimal action values? The ones that we use in kind of our bootstrap over here. So the natural choice, like the easiest one to think of, is to do the same thing. So if we're following an epsilon greedy like policy at the moment, then we choose our next action according to that policy. We still use the epsilon greedy to update that. Or if you use like the argmax of our queues directly, then it's not the epsilon greedy. It's our greedy like actual policy. So if we always use a greedy policy, then we'll hit the same issue we've encountered earlier, which was we don't explore anything, we don't learn about our space. But if we always use our epsilon greedy approach, then in a sense we're figuring out what the optimal epsilon greedy algorithm is, not the optimal. We're figuring out what the optimal epsilon greedy policy is, not the optimal policy. Is it clear that there's kind of like a problem over here? So, it turns out we can actually do what we need to do for both cases. Like, it's possible to find the optimal policy and at the same time explore around. And basically, it'll be more clear when we look at the kind of a very abstract approach, a very abstract view of the whole thing. So we start our state, we take our action, we get a reward, we enter the new state. And then the meaning of this action over here is what we think the optimal future action is, because we're trying to estimate what the optimal future return is using Q. Because to use our Bellman equations, we have to, the Bellman equations only hold when you use the optimal actions or talk about the optimal states. And so the reason why we're choosing an action over here is that we're trying to figure out what the optimal action is to update our values. Whereas the action over here is the one we actually carry out to explore the environment. So this one is used to explore the environment. Is there actually any reason why this one has to be the optimal one? Yeah. About this thing. So for this first A over here, this is the action that we take when we're in a current state. It's like, take this action and then we ask the environment what happened when we take that action. And so the question is there any reason why we have to use the optimal action over here? Remember, this is at training time, not at test time. So we're trying to find the values before we actually use our system and deploy it. So.
Random or epsilon greedy?
Yeah, there's no reason why this one has to be the optimal action, because as we said earlier, we can use an epsilon greedy approach to learn more about the environment. But then for this one, we're using it to estimate an optimal return so that we can update our values. Is there any reason why this one has to be the same as the action we actually carried out earlier? or in the next step, to be precise. So as you can see, these two actions don't actually have to be the same. This one's used to make an update, but then we can say psych and then take a different action instead. And so this brings us to kind of an off-policy learning approach, which is sometimes we can learn what the best actions are even if we don't actually take those actions. Like if we have a homework that won't be graded, we can we don't write the optimal answers. Instead, we write kind of like more risky answers to see whether they pass or not. But then we still learn more about what the optimal answers are. And we can learn by observing what others do, for example. It's also pretty similar to kind of exploring other things. And so instead of just a string of SAR, we kind of have more of a string with little what-if policies attached to it. After each state and action or reward, we're thinking, what if we took this optimal action instead? What do you think our new value will be? But then we actually take a different action after that. And so the actions we take to get our samples are not the same as the ones that we use to get our optimal policy. And hence, we call it an off-policy method. The actions we take are kind of off from the policy that we use to actually explore the environment is off from the one that we're actually trying to learn. And so, yeah, this is to be more clear. We're using our data to improve our actions, but then we use different off-policy actions to collect our data. And so if we do this, we're basically end up at Q-learning, which is kind of one of the most popular classic RL algorithms, and also the deep variant is also pretty big in the field of deep learning. And so this is how Q-learning works. It's basically the same as our kind of abstract view of SARSA. We start off at a state, we carry out our action, which in this case will be the epsilon greedy policy from our current state. Again, we don't have to actually store the policy. We can just infer it using Q. Then we carry out this action for real. We will get our rewards in our state. And now this is our what-if action. We argmax over all of the Qs. And we use it to update our values using the Bellman equation. If we do this long enough, we'll actually converge to the true values of Q. Despite knowing almost nothing about the environment, we don't know rewards, we don't know transition probabilities, we just know Q. But then now we have the optimal policy with the optimal Q. Isn't that pretty interesting? And yeah, it generalizes to the Lambda method as well. And let's see. This is just how we choose our policy, which is at test time, when we actually want to do the greedy policy, we just take the argmax with Q and guaranteed to take that action. Otherwise, when we're exploring, we do an epsilon greedy method. So is everyone clear on how Q-learning works? OK. And now, time to get into more of the real deep stuff. If you think about it, all of our algorithms kind of have a table for either all of the states or all of the state actions. So if you have an infinite number of states, then you have an infinite table, which is not very feasible. So this is actually pretty common. Like in our grid world, instead of a 5x5 grid, what if you actually had a space where you still have only 4 actions, move left, up, down, or right, but then now you're moving up, down, left, or right on this weird surface. Or actually, this is the value function, but you're moving on a square that has dimensions 5 in either side. And so you can't have a table that has a Q value for every position. And even if you kind of discretized it and have a table of 1 million by 1 million, then your algorithms will take forever to converge. So even for example, something like Go, technically there are a finite number of states, but then you'll be having plenty of fun doing a classic RL approach on that. I don't think you can even count up to the number of states, let alone updates to find the optimal values for each one. And so for these continuous states, typically what we can do is we have this parameterized function. Instead of just having one Q value, and we evaluate what the Q value is at a state and an action using a function that has parameters to it, instead of just storing them all individually. And so instead of just writing values to this table, we're kind of optimizing our function to give us a best estimate of it. So this equation should look pretty familiar. You've been looking at it like for the past semester. Anyone tell me what it looks like? This is a gradient descent algorithm. So like this is the learning rate. This is a gradient. We're taking a step towards a negative gradient, which using a divergence function. And so instead of writing to a table saying like this position is this value, instead we're training it saying this position should be this value, improve your parameters to make it more so. And so it's kind of a close analog to writing a position on a table, though you may have to like do it more times to make sure you get it right. And so our parameters can be really simple, like if you have a vector that represents your state and a vector that represents your action, maybe one hot in that case, you can just do kind of a linear function of the concatenation of the two. This is a perfectly valid parameterized function. Simple, but it's true. We can have something really complicated, like these convolutional networks, which eventually produce Q values. The fundamental issue that we have with something like this is that because it's not a table, we can't actually be perfectly accurate. So the table has to like make compromises. It has limited capacity. So with the Q values, once you write into it, it will never change, even after you write everywhere else. But then for the Q function, if you train it once to give you a value at a specific position, and then later you train it in a number of other positions to give you other numbers, there's no guarantee that your original number that you wrote earlier is not going to change. I mean, it probably will. That's kind of what generalization is. And so if we've like trained our function at a specific position, if we don't visit that position for a long time, then it could like we could get a very divergent result at there, which can be a really big problem for something like Q learning, where we're kind of depending on the fact that each position is converging closer and closer to the optimal Q or the optimal values. And so if the Q value is changing while you're learning other Q values, and you're kind of chasing your own tail, you're saying like, I'm going to pretend that this is the correct Q value, and then I learn something else, but then the correct Q value has changed because you're trying to learn something else. And so like with the regular Q learning, it works because even though our sample data will be actually pretty biased, even with epsilon greedy, you're going to have lots of actions that look similar to the optimal policy's actions at some point. But still, like, because we're using epsilon greedy, we'll eventually be visiting every state and every action enough times to get to like converge the correct result. Even if you update a really rare state and action once, and then a million iterations later you update that state and action again, the value you wrote there earlier is still there waiting for you to come back so that you can improve it. It will converge just more slowly. Now with the Q function, let's suppose that we've run several episodes and this is what actions we've taken at various states. If the Q function is going to, like the way it's designed, basically it's going to try very hard to make sure that the common data is accurate. And so if it happens at the expense of the uncommon values, just like the ones over here where we don't visit very often, if we run policies if we run our policy and we move this way many times, then eventually like our estimates over here are going to get very different. And then on the very rare case where we do come here, we'll be starting off basically from scratch again. We can't like work from what we've had earlier. So it's not that just like being able to explore the entire state action space is not enough. We also have to be able to visit them often enough so that we don't forget. So like if we basically force ourselves to take a path that goes through here once in a while, just often enough so that like we like remember what their old Q values were, then maybe slowly we can converge to the correct values, and then we'll get a better result. So I guess does anyone have questions about how this one works? Like what kind of problem we're facing over here? Does anyone have questions? Does anyone have a suggestion for what we can do? Those of you who haven't done deep QNX.
Like LSTM to store some memory about those states.
That's actually really close. Or that might actually be a complicated variant of what would work. So it's the idea of memory. Why do you think like having memory of the states will help?
So you can remember those values for the rare states.
Oh,
So you can, like, start from scratch.
But then the thing is like, if you're saying like we create a table, then we can't create a table since there's infinitely many states. But we can have memory of something. It's just not of the Q values at each position. Like if you have a function approximator over here, then it's another infinite regression problem. Well, we have to worry about what the most common values are in the function, what your function estimate level 2 is. So let's see, what do we have a finite number of? We have a finite number of actions, sure. That's not too helpful though. We have an infinite number of states, yeah. Rewards. A reward is a function that, like, given a state and an action, it's a probability distribution. But we do have a finite number of something related to rewards. We have a finite number of observed rewards because we can only play this game a finite number of times. And so, like, we can have a memory of all of the different things we've done before. So, like, let's suppose we've taken this rare path like once in our history, then we can store it into our history, and then like now we can like go back and say do this path again with your new Q values and see what happens. And so this is what gets us to the action replay idea, is as our original data, it has a lot of bad characteristics. It has like lots of correlation to it. You're going to be all your actions at a given point are going to look like your current policy. It's not going to be really random. And then once your policy updates, it's going to be your actions now are going to look very different from your actions before when your policy was different. And you also have the like uneven distribution problem. Most of your actions are going to look like your optimal or your estimate of the optimal policy's actions. Not going to be like one of those. You have the exploration ones, but they're rare. So instead, we create this buffer of all of our like past actions. And now with this buffer, we can control how we're going to sample these values to our learning algorithm. And so just the pseudocode for how it works. For B, just like a kind of batch number. For B steps, we take our action experiences and put it inside our replay buffer. And then after all of that, we sample from our replay buffer. I guess it doesn't have to be B, but just for consistency, I'm going to take B samples of it, and we update our Q function using this. So we've kind of decoupled the two parts of our system, the part that explores the environment and collects data, and the part that uses the data to improve its estimates. As you can see, there's like no real reason why the two have to use the same data each time. The second part, the part that improves the function, it works best when your data like looks like a random distribution from a fixed data collection, like all of the supervised learning examples you've done before. And so we're basically kind of like emulating that functionality. You can think of this replay buffer as like our fake data set, where now that we have a fake data set, we can use all of our tricks to randomly sample from them and to make sure that we don't get like kind of oscillation issues or correlation problems related to correlation. And so we can have really complicated algorithms for how the replay buffer will sample from things. You can, for example, just make them look independent. That's the normal one. You can basically make it so that the old experiences get sampled more often, or you can make the rare experiences sampled more often, or you can change the frequency depending on how accurate the Q function is at that point. like you can look at the divergence function, and then if the divergence is high, you make a note saying, make this data point more frequent in the future. There's really crazy things you can do with the replay buffer in theory. Now that it doesn't have to be the same as the data you're getting raw. Anyone have questions about this? Okay. And so what is the best way to sample from our buffer? So on the one hand, we don't want to go crazy and like create a random distribution over all states and all actions, because like we still want it to optimize for the more common cases. Like let's suppose we're making a kind of a chess game AI. We don't want if we're using kind of a function approximator to do it, which is not the way we've done it with like Deep Blue or anything. But if we do that, we want to make sure that our function is optimized for common chessboard positions. If we just pick all of our pieces and put them in random places, that's not going to be very common. It'll be kind of silly to make our algorithm work just as well on that case as with a common game. So like on one hand, we do want to actually make it fit closer to common data. It's not completely bad that it does this. But on the other hand, as we said, like if it goes too far, then it'll become inaccurate on the uncommon data, which is going to be a problem. We can't explore the better policies. I mean, we can't learn more about the better policies before they get forgotten. So it's kind of like a trade-off. We have to choose what we have to do. Okay, so this is going on to a different problem over here. So remember how we said that like our data is kind of, well, I guess it's not even that. So when we're doing the updates, we're kind of like chasing a moving target, which is we're using our current values, like action values in our case, to improve our action values. And therefore, like every time we update our action values, we're trying to move to a different place. With the original methods, it's not too bad because every time you do this, you're only updating one state with one action, whereas you can still have a good number of states and actions. So like, though you're chasing a moving target, the target is moving kind of slowly, so it still works out. With the queue functions, it's not the same because when you update your queue function at one position, the whole function will change, even if slightly. And so like, the target values at every queue position is going to be different. It's the entire function will change when you do a single update, and you have a moving target at all infinite states that you're trying to learn. It's a much worse problem over here. Does anyone have a suggestion for what you can do about that? So like, ideally we want to chase a fixed target, but then queue learning doesn't, the reinforcement learning doesn't work if a fixed target, if it's completely fixed. That would be supervised learning if we're just going for a fixed target. And so like, the reason we have this problem is that we're updating our queue values and then we're using it to create target values. So if we make sure that the target values don't change, so like if we create two copies of our queue function, one of which is going to always change while we're learning it, and the other one doesn't change, then like as we're training our queue function, our targets are fixed. We're using the same queue function to like create estimates for the future results. So like rightfully this won't work at all if we never update this target function. Like if we initialize with 0, then this is 0, max of 0 is 0, 0 times gamma is 0, and we'll be getting something completely wrong. So if we never update it, it won't work out. But then if we periodically update the copy to match the one, or it's not periodically, even if it's just following the learning copy more slowly, then like this would help deal with the moving targets issue. And so in doing so, we would be able to converge more quickly. And so like with those two updates, we end up with the deep queue network. So we create a neural network, which is slightly different from the queue network, only in structure. The deep queue network takes in a state, and it would output the queue function or an estimate of the Q function for that state for all of the possible actions. So like if you just want one of them, we can mask away all the other actions and take the one Q value over there. And if you want to do kind of an argmax, you can just take the entire vector and do something with it. So like this is kind of efficiency design. With this design, you can do both the argmax and pick a single value more easily. And then we do what we said. We create a replay buffer, and we have a frozen target network, which we periodically update. And we do Q learning just as before. We still have an epsilon greedy approach. We still choose our action based on the argmax and so on. And then we just remember to sample from the replay buffer and to update our target network to get our new Q values. Is there any question about how deep Q networks work, or any of the two things that we did to it to make it work?
Does it make sense to choose to update the target Q function when the reward is a maximum equal to this one?
So when the reward is maximized over a period of time, oh, as in like when we're nearing convergence. So yeah, once we're nearing convergence, you may want to like change how often you update the target, because like maybe we're moving too slowly and we want to like incorporate our new knowledge as soon as possible. So yeah, that's kind of like I guess it's a pretty important engineering decision to make. Even if you don't do that, it would like, well, I guess this entire deep Q network is engineering decisions too. But yeah, that's a good point to make. Everyone know how they work at least? So here's some like statistics that I found on a website. I don't know what the scale is here, so you can just do comparisons. With the linear network, which is, I think it's a function approximation with a linear function. This is kind of the scores we get on these 5 games. And if we do the deep Q network kind of without those optimizations, then we'll encounter all the issues with the bad sampling and the moving target and so on. And so we do either worse or about the same as the linear function. And now with if we take those optimizations into account, we get 100 times better on breakout, and a few, maybe like 3 to 10 times better on all the other games. And you can figure out, you can like cripple the network specifically in these 2 ways to see how different the results will become. So with neither the replay buffer nor the target function, these are the results we got earlier. If we turn on the target function, we do get a bit better for some of them. If we turn on the replay buffer, we get better on kind of a different classes of problems. If we turn on both, we get like, is this? Yeah, I think this is even bigger than like the sum of the individual improvements. So like the improvement from having both might even be they kind of cooperate with each other for some of these problems. And so kind of some other optimizations we sometimes do with these deep Q networks. First of all, we can change how we compute the Q. So we can compute Q with kind of in 2 parts. First, we have this one value for the state, which is, it's kind of like an analog for our value function, but it doesn't have to actually be the value function. It's just a number we're assigning to that state, regardless of the action. And then on top, we have what is known as an advantage function. So like how, on top of the value of the state itself, how much of an advantage do we get from taking this action? And so like this kind of decomposition can help a lot, because even if the advantage function is just a constant related to the action you're taking, so like in that case, it'll be just a constant vector. Even if it's a constant vector, and even if your combining function, f over here, is just addition, you can still get a pretty good estimate of Q, like something you can start with. Then you could tweak the advantage function to take interaction effects between state and action a little more. And so like, this is so it helps the kind of the neural network have a sub goal to work towards before making finer improvements on top of that. And also, there's a separate issue, which is with our deep Q networks, they don't give you the perfect Q values. so if you take a maximum over a bunch of actions, you'd be taking a maximum of something that has noise added to it, which can skew how you do, like what kind of result you get. And the whole, if you remember how we do gumball noising, like we can significantly affect how maximum works just by adding noise to the data. And so like this maximum could be like a bias towards a large value. The ones that have like very big noise or something could make the noise dominate the max operation, even if the Q function is usually pretty small for it. And so the solution we do is it's called a double DQN, which is we train two of these DQNs at the same time. But when we do the max operation, instead of taking the max action of the Q values directly, we take the argmax of the Q values for that network, and then we use the second network to figure out what the Q is at that position. And so it's kind of like the noise affects what action you pick over here, but then it still figure out you have a different noise profile for when you'd use the second DQN on it, which can help helps bias the network less with the way the max works. And similarly with the second DQN, instead of taking the max of all the actions in the second DQN to update itself, we use the first DQN we use the argmax with the first DQN, and then we figure out what the Q value is for that state and action using the second DQN. And so the two networks interact with each other at these points, but otherwise they're trained the same way. Alternatively, remember that we have a target function and a learner function. Instead of just taking the maximum with the target Q function, we can take an argmax with the target Q function and use the learner's Q function on top of that. It'll slightly reduce it'll make the moving target problem a little worse, but some people have reported success doing this. So, and so there's finally one entire family of approaches that I haven't covered. It's kind of a direct policy estimation. So instead of estimating Q values for a function for every state and action, and then taking the argmax over the action, you can just make a network that takes in the state and directly outputs an action. So it's this network would be known as a policy network, and training it is it's called a policy gradient. And this is more useful when the action space is continuous, because with the DQN stuff I talked about, we still assumed a discrete set of actions. But we can still think about what you can do with continuous actions, but you lose some of the benefits with it. Well, with policy gradients, it doesn't really care whether your actions are discrete or not. You can use policy gradients either way. And I think in the recitation, this was covered much more in detail, like the one last Friday. So that's about it for that. I don't know personally very much about it either, so that's that. And so that's kind of the entire presentation. We talked about the model-free control, and we got into deep Q networks. And anyone have questions? Does anyone want to talk about what the syllabus said we had, the new approaches?
Did you ever cover reinforced? Did I miss it?
No, I don't think so. That's the policy gradient method, right?
It was the standard, I thought we do it.
Oh, in the recitation. I think there might actually be that. Like the one last Friday. I believe Ryan did talk about reinforced then. Is that the one where you have log of the probabilities times? Okay, yeah. Let's see. Does anyone have kind of the end of this?
Watch a Mario video.
Oh, yeah. Let's see if we can find one of those. Let's see if we can find one. Do people use DQNs for Mario?
Yeah.
Okay.
Apparently, model-based feedback.
Let's see.
MARI/O.
Oh, is that? Okay.
It's MAR
Wait, it's live? What?
Yeah, apparently AI playing Super Mario Brothers is live now. It's just, I am curious what that is.
All right, cool.
I don't know,
Games, you can
but-
watch computers play video games.
Yeah. Running computer, watching computer play.
Last I remembered, Mario was actually it was kind of a evolution algorithm, wasn't it?
Yeah, they're a ton of content on that.
It's not too bad. It is bumping into a wall, but I think it'll jump at some point.
Yeah, as soon as that.
You can post a link on too.
Oh yeah, so reinforcement learning is fun. You can do all kinds of cool stuff, such as.
I think another common problem people do is like kind of Doom, I think. Exploring a room in Doom.
Yeah, there's been a lot of Doom, right? And
Mhm.
recently it's been like Dota and League of Legends and
Oh, yeah.
like the harder stuff.
I actually seen once like really good gameplay on Super Smash with deep learning. With just one character, and still not pro level, but surprisingly good. Let me see if I can find it.
But that looks not fair because it doesn't take any moving lag time.
Oh yeah, that one. I think yeah, it's like it makes instantaneous choices too. Is it there though? AI. Yeah. It's just skips right to the middle. The AI is.
Oh, I remember that one.
Yeah, I think the AI is the blue one.
Ridiculous. Like, you cannot kick someone off the edge that easily.
But the AI is actually pretty good. I think its main benefit is that's really good at dodging everything. Yeah, so it plays pretty well on that too. See, what other problems are there that people have done? Do you know much about actor critic? I actually don't. It's like one of the optimizations you can do on neural networks for deep reinforcement learning. Okay, never mind then.
It's been a long day.
Yeah.
That's
Okay, yeah, so there's no questions then.